This
work
conference will now be recorded.
controller. So in order to understand the concept of timers, we had to study few important terminologies. So the first one we saw was resolution, which is nothing but the width of the timer register. Then we saw tick, which is nothing but the change in the value in the timer register. So the change from 0 to 1 is referred as tick. The change from 1 to 2 is referred as tick. So you can either do an upticking, saying that one tick covered, two tick covered, three tick covered, and so on. Or you can also do down ticking, saying that there is 255 ticks remaining, 254 ticks remaining. So that way you can do the down ticking also. Then after that, we also got to know something called as quantum. The time taken for a tick to happen is called as quantum. It depends on different factors in each of the devices. In some of the devices, it is going to depend on system clock settings. One such example is our PIC16F877A microcontroller. So the quantum is directly proportional to the system clock settings, which is nothing but the instruction cycle time. So in case of our PIC16F877A microcontroller, one instruction is going to take 4 cycles for its execution. Hence, quantum is nothing but 4 divided by F oscillating frequency. F oscillating frequency is 20 megahertz. Then after quantum, we got to know that whenever you take a timer whose resolution is of 8 bits, so you are going to So we saw that when it comes to the timer, in case of our microcontroller, the how much is the quantum? How much is the quantum of our microcontroller? Come on, how much is the quantum of our microcontroller? Yes, it is 200, not microseconds. It's 200 nanoseconds. So one instruction cycle or one instruction takes 200 nanoseconds for its execution. So according to this, if you take a timer register of just 8 bits, understand that the resolution, if it is just of 8 bits, the maximum you can store is 255. So after 256 ticks, it is always going to get an interrupt generated. So that way, it can count only 51.2 microseconds. So an interrupt gets generated for every 51.2 microseconds. In that case, the main application is going to get disturbed. It will not get enough time for the main application to get executed. So sometimes we may have to delay the process of control going to the ISR. So as it was going very frequently for every 51.2 microseconds, you may have to extend it to more number of time. That is when you can use scaling. So some of the microcontroller supports pre-scaling, some of the microcontroller supports post-scaling. So either of the scaling will be configured in case of any given programming. Some of the microcontroller supports both pre-scaling and post-scaling with different scaling ratios. So when it comes to the pre-scaling, the changes what you are making is with respect to the instruction cycle. So when it comes to the pre-scaling, for every tick, there was 200 nanoseconds consumed. But if you go with the pre-scaling ratio of 1:2, so one tick is going to happen after 2 instruction cycles. If you go with a scale of 1:4, one tick happens after 4 instruction cycles. So that way you can delay the process of control going to the ISR using pre-scaling. If you do the same using the post-scaling, so that you are going to count the number of overflows. So if 1:1 is the ratio you are going to take or scale you are going to take, so one interrupt gets generated after every overflow. If you take 1:2 being the ratio or being the scale, then one interrupt gets generated after 2 overflows. So that way you can actually delay the process of control going to the ISR. Apart from that, We just briefly saw what are the different modes a timer can be configured. So a timer can be configured as a counter. It can be used in pulse width modulation or pulse generation. And you can use the timer also in pulse width measurement or pulse period measurement. So we started discussing the examples. We looked into the first example of the timer. This was the requirement provided. You had to generate 5 pulses of 8 microseconds. The resolution has to be 8 bits and quantum has to be 1 microseconds. So we saw that whenever we want to get the interrupt generated earlier or more frequently, the only way is when you come to the microcontrollers, when you come to the interrupts generation with respect to the timer, always there has to be an overflow from 255 to 0. If you take a 8-bit register, always there has to be an overflow made from 255 to 0. Only then the interrupt is going to get generated. Now, if you want the interrupt to get generated early, then you just have to make sure the timer register is loaded with some value so that interrupt is getting generated earlier. That means you have to make sure the overflow from 255 to 0 is happening a little faster. So you are going to keep track of it and then preload the timer register with some value to make sure interrupt is being generated on a early basis. So that is what we discussed in the previous class, how to generate a time, like a smaller time, approximately 4 microseconds of on period and 4 microseconds of off period. Now let us continue with one more example. So what we generated was a very small time of 4 microseconds only, 4 microseconds being the on period and 4 microseconds being the off period. Now let me go with one more requirement to be done here. And the requirement this time we are going with is you have to generate a larger time. And trust me, larger time in the sense it is pretty large. So I would say it is 1 second. Okay. So the question is you have to toggle the LED for every 1 second. Okay, so you have to toggle the LED for every 1 second. So that is the requirement. Now we have already known the logic of toggling the LED, but we have not achieved the exact time of 1 second. We were just using some blocking or non-blocking delay, but we are not sure whether it was exactly giving me 1 second of delay or not. So I want to toggle the LED for every 1 second, and that 1 second of time I should be achieving with the help of the timer. And this time, let us consider our own timer, the timer of the PIC microcontroller. So first and the foremost thing, let me just give an assumption of the resolution because we have not known the resolution yet. So resolution I'm going to provide is 8 bits. Okay. So that means the timer register's size is of 8 bits. Now after the resolution, the next thing I have to consider is quantum. So how much is the quantum in case of our microcontroller? I'm asking you things repeatedly because it is really important. So how much is the quantum of our microcontroller? Yes, it is 200 nanoseconds. Okay. Now, after how much of time interrupt is getting generated in case of our microcontroller? If the quantum is 200 nanoseconds, after 256 ticks, that is right. That means how much is the time covered? Yes, so it is 51.2 microseconds. Okay, so this is the requirement provided. So you are supposed to toggle the LED for every 1 second. Now let us start with the programming part. So I'm going to start with the main function. Okay, so void main function. Now being in the main function, the first task I want to perform is to turn on the timer. Okay, so I have to turn on the timer now. 1 second. Okay, so I'll go with, yeah. void main. So I'm supposed to turn on the timer because I want to achieve 1 second of time. So as a statement, I'm going to write it as turn on the timer because we have no idea how to turn it on yet. Then after this, I'm going to write is a while of 1. Okay. Then you have got the timer which is running, and after 1 second, I actually have to toggle the LED. So let me take a variable called LED, which is maybe connected to RD0 or RB0, whichever you are comfortable with. So assume there is a macro called LED, and for this LED, I'm initially having the value 1 return. Okay. So if you are confused with this, let me also write a macro as define LED as let's say RD0. Okay. So I have an LED initially returned with the value 1. Now the timer has turned on. After 1 second, after 1 second of time has been achieved, I have to toggle the LED. Now tell me, when the timer has been turned on, it is going to generate an interrupt. So when an interrupt occurs, where will the control go? When an interrupt occurs, where will the control go? Yes. So it has to go to the ISR. So ISR is a void function. So I'm writing an ISR here. And being in the ISR, the first thing I have to do is I first have to check if I came to the ISR because of the timer register. So I'll write if TMR IF is equal to 1, because once you have come to the ISR because of the timer, your microcontroller will set its flag bit to 1. So I am checking, I'm making sure if I came to the ISR because of the timer. So I'm checking if TMR IF is equal to 1. Now if this is equal to 1, that means I'm supposed to perform the operation of toggling the LED. So in order to toggle the LED, okay, so I'm going to write it here, that is toggling the LED. So LED is equal to right, not of LED. Okay, so I'm writing this. And I should not forget to make TMR IF back to 0. Okay, so that is the task of mine. So before coming out of the ISR, I have to make sure its flag has been set back to 0. So I'm writing TMR IF is equal to 0. Now see how this is working. Initially, timer has started counting the time. So we are going to make use of a register. So this is the timer register. And according to the requirement, the size of this timer register is 8 bits. So TMR, which is of 8 bits. Now, if it is 8 bits, how much is the maximum value I can store? If it is 8 bits, yes, 255 is the maximum value. After there is an overflow from 255 to 0, there will be an interrupt getting generated. So I can store a maximum of 255. Now the timer has been turned on. Because the timer has been turned on, so your timer register is going to start counting the value from 0. So after 200 nanoseconds, it counts 1. After 200 nanoseconds, it counts 2. Then for every 200 nanoseconds, a tick is going to happen. Then after 255, there will be an overflow made to 0 and interrupt gets generated. Now, when the interrupt gets generated, control will go to the ISR. Okay. And I'm going to check if I came to the ISR because of TMR IF. Then the condition is true. I'm going to toggle the LED. TMR IF is made back to 0 and it comes to the while of 1. Again, your timer has not stopped. It has continued to count from 0 all over again. So from 0, again it starts counting 0, 1, 2, 3. So that way it is going to reach 255. Then an overflow will be made to 0. Again interrupt occurs, control goes to the ISR and LED will be toggled. Now if you actually observe this program, Tell me, for how much time am I toggling the LED? For how much time I'm toggling the LED? Am I doing it for 1 second? According to the program we have written. After how much of time the toggling of LED is happening? Yes. So whatever program I have written is getting an interrupt generated for every 51.2 microseconds. So for every 51.2 microseconds, I am actually toggling the LED. For every 51.2 microseconds, control is coming to the ISR and I am toggling the LED. Now, think of this and answer. What I wanted was 1 second of time. But what I have achieved right now is 51.2 microseconds. Answer me whether the time I have achieved is smaller or larger than what I require. Whether the time I have achieved. Yes, the time I have achieved is smaller, but I actually want 1 second of time to be achieved. Now, as of now, it is going to the ISR for every 51.2 microseconds. Actually, for how much time should the control go to the ISR? After how much of time I have to go? Yes, after every 1 second, I want the control to go to the ISR. I want the interrupt to get generated after 1 second. But it is quite challenging. So obviously some of you have started answering it right. Yes, we have to make use the concept of scaling. So because we have to delay the process, as of now it is going for every 51.2 microseconds. I have to delay the process, so I have to use the scaling. So whichever you are comfortable, whether it is pre-scaling or post-scaling, it can be used. But the problem is, I don't know whether my controller supports pre-scaling or it supports post-scaling, or what if none of the scaling is supported by the microcontroller. It is going to vary from one device to another. So as of now, it is going to the ISR for every 51.2 microseconds. It is right that I have to use the scaling in order to delay the process. But I don't know what is the ratio available in my microcontroller or what is the scaling option available in my microcontroller. Whether it supports pre-scaling or post-scaling, we don't know. So what we are supposed to do is, I have to make sure the toggling of LED is happening for every 1 second. Okay. So I have to make sure toggling of LED is happening for every 1 second. So what I will do is, instead of choosing the scaling option, I may come to the ISR for every 51.2 microseconds. But I will not take the action every time I come to the ISR. Instead, I will take the action only after 1 second of time has been achieved. Now, how to do that? You please observe. I'll add certain things here. So, I will actually take a variable called count. Okay, so I'll take a global variable called count here, and let me have it initialized with the value 0. Okay, so I'm taking a variable called count, a global variable which is initialized with the value 0. So here I'm going to add a statement. If, okay, so I would say plus plus count is equal to some value. Okay, only then I will toggle the LED. First I will make count value return with the value 0 back, and after this I have to write it like this. Okay, now please observe. So count is initially returned with the value 0. Okay, so as of now count is 0. Now after 51.2 microseconds, control comes to the ISR. You check that you came to the ISR because of the timer. You're doing plus plus count. Now if the count value is 1, okay, if the count value after I do plus plus count, if it is 1, How much time is covered? If the count value is 1, how much time is covered? Yes. So if the count value is 1, so the time covered is 51.2 microseconds. Okay. Next, should I take the action now? When the count value is 1 and time achieved is 51.2 microseconds, no, I should not take the action. So I will not enter into the if block. I will make the flag bit set to 0 back and I will get back to my while of 1. Again, after 51.2 microseconds, one more interrupt occurs. So you come to the ISR. This time the count value will be updated to 2. Now tell me, if the count is 2, how much is the time I have achieved? How much is the total time I have achieved? Yes, so another 51.2 microseconds are covered. So total of 102.4 microseconds. Now I still have not achieved 1 second of time. So again I will come out of the ISR. Again after 51.2 microseconds, when count takes the value 3, how much is the total time achieved? How much is the total time achieved when count value is 3? Okay, so 153.6 microseconds. That is right. Now this way, I did the trial and error method. So when the count value is 20,000, okay, when the count value is 20,000, how much is the time achieved? I did some trial and error method. So when count value is 20,000, can you guess how much is the exact time achieved? Yes, that is close to 1 second. Oh. Yes, so it is 1.024 seconds if I'm not wrong, right? So it must have been 1.024 seconds. Okay. So the time covered here is, let me make a note of it. It is 1.024 seconds. So now I can make a comparison of count with 20,000. Okay. I have approximately achieved 1 second of time. So I am going to toggle the LED. Okay. So I'm not going to take the action every time I visit the ISR. I will take action only after 1 second of time is being achieved. So when I go with while of 1, so for every 51.2 microsecond, I may visit the ISR, but only after count reaches 20,000, I would have achieved approximately 1 second of time. So I am going to take the action accordingly. So when count reaches 20,000, I have approximately covered 1 second. And now I'm going to toggle the LED. So this way, don't you think I'm toggling the LED for every 1 second? So I understand that we can use the concept of scaling, but I'm not using it here as I don't know which scaling will be available in given microcontroller. Some of them supports pre-scaling, some of them supports post-scaling, some of them supports things like a certain scale only they will support. So they may support 1:4, 1:16 only, something like that. So it varies from controller to controller. So I'm not writing it for one specific microcontroller. Hence, if I write it like this should be working fine for any given microcontroller with a quantum of 200 nanoseconds. Is this clear? Okay. Now I will have a small formula return. So the time I have been calculating. Okay. So I would say time, whatever I'm achieving is dependent on, I would say total number of ticks. Okay. So total number of ticks. Okay. Multiplied by quantum multiplied by, I can also say it depends on count as well, right? So I can also say count. And also further, if you choose any scaling, it also depends on scale. So the time you are going to achieve is total number of ticks, okay, which is used to have an interrupt generated, multiplied by quantum, multiplied by count, multiplied by scale. Now, if the ratio of scale you are using is 1:2, in the calculation, scale can be substituted with just 2. And if you are using a scale of 1:16, in the calculation, you can use the scale as just 16. Because you can see here, if the scale is 2, okay, the time is 51.2 microseconds multiplied by 2. If the scale is 1:4, the total time achieved is 51.2 microseconds multiplied by 4. Okay. So if it is scale you are using, you can directly multiply it with the scale. So the total time achieved is total ticks multiplied by quantum multiplied by count multiplied by scale. Okay, I'm repeating again. You see, whether it is pre-scaling or post-scaling you are using. Okay, so generally interrupt gets generated for every 51.2 microseconds. If you are using a scale of 1:2, interrupt gets generated for every 102.4 microseconds. So whether it is pre-scaling or it is post-scaling. Then if it is the ratio 1:4, so whatever is the interrupt getting generated, it is after 204.8 microseconds. So that is actually 51.2 microseconds multiplied by 2, 51.2 microseconds multiplied by 4. So if you take the ratio of 1:8, then 51.2 microseconds multiplied by 8. Okay. So time you are going to achieve is total number of ticks multiplied by quantum multiplied by count also multiplied by scale. Any doubt in this formula? Okay. Now, if you actually see the count 20,000, if I take count as 20,000, the time I'm going to achieve is 1.024 seconds. It is exactly not 1 second. I have achieved a little more compared to that of 1 second. I have actually achieved 1.024 seconds. And trust me, when it comes to the embedded systems design, even 24 microseconds plays a very important role. So I wanted exact 1 second of time, but what I have achieved is 1.024 seconds. So you please do the calculation here, okay, with respect to the count. How much should be the count to achieve 1 second of time? So count should be equal to the time divided by time you want to achieve divided by total number of ticks. Okay. So multiplied by quantum multiplied by scale. Okay. So you please do this calculation and tell me how much is the count I have to take for 1 second of time. So it is count is equal to, so the time I want to achieve is 1 second. So I will keep the time as 1. Then total number of ticks is nothing but 256 multiplied by quantum is 200 nanoseconds. Also multiplied by scale, you can keep it as 1. After you do this calculation, can you tell me how much is the count? After I do the calculations, please tell me how much is the count. 19531.25. Okay, 19531.25. Okay, so I'm assuming the answer is right. So it is 19531.25. 0.25 in order to achieve 1 second of time. Now tell me, to exactly achieve 1 second of time, can I compare the count value instead of 20,000 with 19, I'll write it down here, with 19531.25. Can I do the comparison like this? Can I compare count with 19531.25? Is it possible to do the count comparison with 19531.25? No. So I have to take an integer value itself. Now assume I will round it off. So instead of 19531.25, I will round it off to 19532. Okay. So just assume I'm going to round it off to 19532. Now after I round it off to 19532, don't you think I will achieve a little more time than that of 1 second? If I round it off to 19532, am I not achieving a little more time? Obviously, yes. So you will think, instead of rounding it off, let me make it 19531 here. You will say we will do masking, we will ignore that 0.25 and let us just keep it as 19531. Now don't you think the time achieved is little smaller than 1 second? Is it not little smaller than 1 second? Yes. Now, please make adjustments here and give me the count as 20,000. Okay, means actually an integer value. Make some adjustments here and give me an integer value for the count. So can you be changing the time? Can you change the time in this calculation? No. So time I want is obviously 1 second. So you cannot change the time. Can you change the quantum here? Can you change the quantum here? No again, because quantum is fixed to 200 nanoseconds. I cannot even change the scale because as of now I am not using the concept of scaling. Can I change the total ticks? Can I change the total ticks here? Come on, think and answer. Can I change the total ticks? Yes. So you saw yesterday, I mean in the previous class, you saw that the total ticks I used was just 4. Okay, in just 4 ticks, I got an interrupt generated. So yes, you can change the total number of ticks if you want. Now please make the adjustment to the total number of ticks and give me a whole number as an integer. How much ticks will it consume for the second nested if block, pre-increment and integer comparison? So here, if Chaitanya, you are asking how much tick it will consume for 2 nested if blocks. So for this condition, it consumes 1 instruction cycle. This increment consumes 1 instruction cycle. That comparison takes another instruction cycle. Okay, I'll come to that point. Yes, people, did you find out count being a constant integer? If I want count to be constant integer, please make changes to the total number of ticks and answer. So count should be 1 divided by, I can change the total number of ticks. You tell me how much should be the total number of ticks for me to be taken. Multiplied by 200 nanoseconds multiplied by 1. Anybody there who did the calculation? Okay, any calculations? 2500, what is 2005? 2500? Please check, is it 2500? So you have to tell me what should I take for total number of ticks so that I get count as a constant value, a constant integer. -20,000 with -6 offset. So, okay, 250 ticks, right? So if you take 250 ticks, what happens? If you take the ticks as 250, how much will be the count? 250. How much will be the count? So yes, we will get it as 20,000. Okay. So when you take the total number of ticks as 250, you will get it as 20,000. Now there is a small question. I have to get the interrupt generated for every 250 ticks. How is it possible? I have to get the interrupt generated for every 250 ticks. How is it possible? Like, how can I make sure I get the interrupt generated for every 250 ticks? Yes. Okay. So if you write TMR with the value 7, okay. So if you take TMR with the value 7, so 7 to 8, you will take one tick. 8 to 9, you take one more tick. 9 to 10, you take one more tick. So that way, when overflow happens from 255 to 0, you will cover only 249 ticks. Okay. So to know what is this, yes, it has to be 6. It shouldn't be 7, it has to be 6. It has to be always 256 minus the number of ticks I want to achieve. So it has to be starting from 6. So 6 to 7, 7 to 8, 8 to 9. That way overflow happens from 255 to 0. Now tell me, where should I write this TMR with the value 6? Where should I write the TMR with the value 6? Okay. So first, the moment I turn on the timer, I have to write TMR with the value 6 because every time I want the interrupt to get generated after 250 ticks only. So when I write here TMR with the value 6, first thing. Now inside ISR, where should I write TMR with the value 6? Where should I write TMR with the value 6? After what statement? Come on. Where should I write? TMR IF. Okay. So you have to be writing it here. TMR is equal to 6. Okay. Now understand how this is working. If the interrupt is getting generated after 250 ticks, how much is the total time covered? If the interrupt is getting generated after 250 ticks, how much is the total time covered? Come on, 250 multiplied by 200 nanoseconds. Yes, so that is 50 microseconds. Okay, so you have covered 50 microseconds. Now see, TMR is written with the value 6, 6 to 7, 7 to 8, 8 to 9, 9 to 10. So that way overflow from 255 to 0 happens in just 250 ticks. So 50 seconds of time is achieved. Control will come to the ISR. So 50 seconds of time is achieved. Okay. Then I'm checking if TMR IF is equal to 1. So I am loading TMR with the value 6. Again, I'm going to start with 6. 6 to 7, 7 to 8, 8 to 9. The timer is ticking. Meanwhile, if you see the count value here, it will just be 1. 1 equal to 20,000 will be condition false. So you will not enter into the if block. So you will come out of the ISR. Again, after 50 microseconds, control will go to the ISR. After count reaches 20,000, you are supposed to take the action. Okay. TMR is equal to 6. Why is it random? So it is not random. We made the calculation, and according to the calculation, I want the interrupt to get generated in just 250 ticks. So as of now, interrupt is getting generated after 256 ticks only. But I want the interrupt to get generated after just 250 ticks, which is why we are loading the timer with 6. We can skip initialization of timer before entering the while and keep only in ISR pin. Will be in steady state before. Okay. So what happens if you don't write TMR with the value 6 initially is, you will start from 0. Okay. First interrupt gets generated after 51.2 microsecond. Okay. So in that case, instead of you achieving exact 1 second, you are achieving 1.2 microseconds more. Okay, if you don't write this TMR with the value 6 before while of 1, so that is not going to help you achieve exact 1 second of time. How did we get 250? So it is just trial and error method. So you have to keep doing the trial and error method. So like when count has to be an integer value, the total number of ticks you are supposed to cover is 250 only. Is this clear? So this is how you are going to make sure an interrupt is getting generated actually here for every 50 microseconds, but you are going to take the action only after 1 second of time is achieved. So by this I can say you have achieved an exact of 1 second of time. But actually there is a small problem here. So you will not achieve 1 second of time exactly. There is some challenge which is also associated here. Okay, let me make you understand that. Assume your timer has started from the value 6. So 6 to 7, 7 to 8, 8 to 9, then an overflow from 255 to 0. How many ticks did it cover? How many ticks did it cover if I start taking from 6? Okay, yes. So it covered 250 ticks. Now, after there is an overflow from 255 to 0, where is the interrupt? Where is the control going? Where is the control going? Yes, control will go to the ISR. Meanwhile, what is written in the timer register now? What is written in the timer register now? No, it is not 6. There was an overflow from 255 to 0. There is just a 0 return in the timer register. You just did an overflow from 255 to 0. So timer register is returned with 0. Now tell me, timer has been returned with 0 and you are calling the ISR function. Do you remember what do we call technically if a control goes from function call to function's definition? Do you remember what do we call technically if a control goes from function call to function's definition? Yes. So that is something called as context switching. Okay, so that is context switching. So assume your function call is done here. So your microcontroller is the one who called the ISR function. So function is called, control has to go to the function's definition. Now assume for the CPU or for the processor to go from the function call to function's definition, it is consuming maybe 2 instruction cycles. So I don't know how much instruction cycles it will consume. I'm roughly giving an example. Assume it is going to take 2 instruction cycles to make a jump from function call to function definition. Now, if 2 instruction cycles are utilized to make a jump, what happens in the timer register? Is it still having a 0 itself return? If I have consumed 2 instruction cycles, do you think I still have a 0 itself return in the timer register? No. 2 instruction cycles will cover 2 ticks. So there will be a tick from 0 to 1 and one more tick from 1 to 2. Are you able to follow this? Okay. Now, yes. So ISR function got called. So control is making a jump from function call to function definition. Assume it took 2 instruction cycles. So my timer register did 2 ticks from 0 to 1 and 1 to 2. Now when you come inside this ISR, the first thing you're doing is to check if TMR IF is equal to 1. So that is consuming one more instruction cycle. So one more tick gets completed. Then you are checking, you are assigning TMR with the value 6. So that consumes one more instruction cycle. Then it will start from 6. Okay. Then it will start from 6. 6 to 7, 7 to 8, 8 to 9. Now tell me, by the time you get an interrupt generated, after there is an overflow from 255 to 0, do you think you have covered just 250 ticks? Do you think you have covered just 250 ticks? No, right? So I have missed 4 more ticks here. In fact, 1, 2, 3, yes, 4 ticks. So I have missed 4 ticks here. So the next interrupt which I'm getting generated is after 254 ticks. Okay. So I have to make use of these ticks also which are already covered. So I cannot write here 10 directly because I don't know exactly if it takes 2 instruction cycles only. I'm just giving you an example. So instead, what I can do is, instead of having it return with TMR plus 6, I will write whatever TMR initially had, I will use that also. So I'm going to take TMR is equal to TMR plus 6. So this way, I'm making sure the first 6 ticks are skipped. I just want 250 ticks to be covered. Okay. I have to make sure interrupt is getting generated after every 250 ticks only. So now what happens is, if you observe, when you make a jump from this to here, okay, control from function call to function definition, you start from 0. Assume to make a jump you are consuming 2 instruction cycles. So 1 and 2 are already covered. Okay. Then after that, to check one more condition, one more instruction cycle is covered. Then actually to make this addition operation, one more tick is covered. Then to make the assignment operation, one more tick is covered. So now I have to skip 6 instruction cycles. Okay. I have to make sure interrupt is getting generated after 6 instruction cycles. So how to skip 6 cycles? To this I'm going to add 6. Timer already had 5. I'm going to make it to 11 right now. After 5, it starts from 11, then 12, then 13, then it reaches 255 and it overflows to 0. So that way I'm making sure interrupt is even getting generated after 250 ticks only. So this is how you will achieve 1 second of time whenever you have to toggle an LED for every 1 second with the help of timer. Did you get this? Everybody, are you following this? Okay. There's a doubt. Let me read out. Resolution in quantum, will be different for different microcontrollers? Yes. If yes, then how can we work it on different microcontrollers, or do we have to make changes according to the microcontroller? Yes. So resolution is going to vary from one controller to another. Quantum is going to vary from one controller to another. The ideology behind generating the time will remain the same, but calculation wise, you have to use the values according to the microcontroller and reach out to a constant value. Okay, fine. So that is how we are going to generate 1 second of time, and I'm hoping that you are clear with this. If you have got any doubts, please let me know. Let's take a break of 2 minutes and we will continue with the programming part. I mean, we will execute it and see the programs. All the requirements data will get from the data sheet. Yes, so you will get all the requirements data from the data sheet. Okay, take a break. We will continue. Okay, can we continue? All right. So we will start with the programming of our microcontroller. So let us start with the programming of the timer available in our microcontroller. So which document should we be referring to know how many timers are available in our microcontroller? Yes, we have to refer the data sheet. So I'm taking you to the data sheet here. First, we will look at the table of contents and then we will decide what to start with. So look at the table of contents and answer me, how many timers does our PIC16F877A microcontroller has? How many timers does it has? Yes. So it has 3 timers. Okay. So first one is timer 0, second one is timer 1, and third one is timer 2. So our PIC16F877A microcontroller has 3 different timers. So you can use all of them whenever it is required. Now let us start with the configuration of the very first timer, which is nothing but TMR 0. Now please read the information regarding the timer 1. Okay, so I think this much you can read with respect to the timer 1. I mean timer 0, and then we will continue with the programming part. Please read it and let me know once you're done reading it. Okay, done. Okay. So let us start listing some of the features of the timer 0 module. So to start with, we are starting to configure the timer 0 module. How much is the resolution? How much is the resolution of the timer 0 module? Yes, it is 8 bits. That means how much is the maximum value you can store? If it is of 8 bits, yes, the maximum value you can store is 255. Then the next thing what it says is the register is readable as well as writable. So the timer register you are going to deal with is readable as well as writable. Then it is an 8-bit software programmable prescaler. Now tell me, do you think the timer 0 has post scaling option? Does it have a post scaling option? No, it has only pre-scaling option. Okay. So what ratios of pre-scaling are allowed? We will see going ahead. Then you have internal and external clock select. Okay. So you can either make your timer work with the help of an internal clock, or you can make your timer work with the help of an external clock. So actually, this timer 0 can be configured as a timer or it can be configured as a counter as well. Okay, so timer 0 can be configured as a timer, it can be configured as a counter as well. Now, if you are making use of internal clock for the ticks to happen, so that is you are configuring timer as a timer. Okay, if you are making use of internal clock for the ticks to happen, that is your clock frequency, then you are configuring timer as a counter. instead of internal clock, if you are going to make a tick happen according to the external clock, then you are configuring it as a counter. Okay. So if you are using it as an external clock, then you are configuring it as a counter. So we will see an example of how to configure the timer as a counter. So like after a few more examples, we will get back to that. But just remember that the timer 0 can also be configured as a counter with the help of an external clock. Then you can see there is an interrupt on the overflow from FFH to 00H. So FFH it is saying things in an hexadecimal format. So interrupt always gets generated after there is an overflow from 255 to 0. So after there is an overflow from 255 to 0, there is an interrupt getting generated. Then edge select for external clock. Let us not concentrate on external clock right now because we are going to configure timer as a timer right now. Now, whenever you have to make use of a timer, okay, so timer is like a module, it is like a peripheral which is going to calculate the time. Now, in order to work with this timer 0 module or any peripheral which comes in your microcontroller, if you want to configure any of the peripheral, please understand that each peripheral will have some registers associated to it. Okay. Every peripheral you are going to configure, every built-in peripheral you are going to configure of your microcontroller, it will have a register associated to it. It will in fact have a set of registers associated to it. So you can make use of those registers. You have to make use of those registers whenever you have to configure that particular peripheral. Now, how to know what and all registers are associated to that particular module? You just have to scroll down to the end of that module. Okay, you just have to scroll down to the end of the module. So if you can observe here in this case, okay, I'm scrolling down, I'm taking you to the end of the timer 0 module, which will give me a list of the registers associated to it. Okay, you can see here table 5.1, the registers associated with the timer 0 module. You can see a list of registers associated to the timer 0 module. Now you can see I have three registers associated to the timer 0 module. So one is TMR0, so that is timer 0 module register. So as of now, until now actually, whenever we were taking the timer register's name, we kept it as TMR. So with respect to the timer 0, the name of the register is TMR0. Okay, it's an 8-bit register. Then we have something called as intcon register and also something called as the option register. So these are the registers which are available, which are associated to the timer 0 module. Can you see some of the bits? Actually, if you see for the registers, it has got 8 bits. Okay, the size of the register is 8 bits. This is bit number 7. This is bit number 0. So every register you can write all 8 bits at once, or you can write it into individual bits also. Individual bits have also been given with the name. You can write it with individual bits also. So that is why we say the registers are bit accessible as well as byte accessible. You can access a particular bit, or if you want, you can write a complete byte also. Now, if you take the intcon register, it's a 8-bit register. Bit number 7 is named as GIE. Bit number 6 is named as PEIE. Bit number 5 is named as TMR0IE. Bit number 4 is named as INTE. Bit number 3 is named as RBIE. Bit number 2 is named as TMR0IF. Bit number 1 is named as INTF. and bit number 0 is named as RBIF. Then coming to the option register, the 7th bit name is RBPU, 5th bit name is T0CS, then 4th bit name is T0SE, 3rd bit name is PSA, 2nd bit name is PS2, 1st bit name is PS1, and last bit name is PS0. So this table represents the default value when there is a power out reset or brown out reset. So this is the default value when you're doing all the resets done. Now, can you observe some of the bits are in gray background? Can you observe some of the bits here are in a gray background? Yes? Okay. So that is because here onwards, not just in this particular module, whenever you are dealing with any given register, and if you see some of the bits being represented in gray background, please understand that those bits will not belong to the peripheral you are focusing on. So here if you see INTE, then RBIE, INTF, RBIF, RBPU, INTEDG, they do not belong to timer 0 module. They are in fact belonging to some other peripheral. So can you remember where did we use INTE, INTF and INTEDG? Where did we use them? So yes, we actually use them in the external interrupt. Okay. So we actually use them in the external interrupt. So whichever bits are in the gray background, please remember that they don't belong to that particular peripheral. So you don't have to focus on those bits which do not belong to that particular peripheral. Okay. So the name of the timer 0 register is TMR0, and the name of the timer 0 interrupt enable bit is TMR0IE. So if you want to configure timer 0, if you want the interrupt of the timer 0 to be enabled, you have to write TMR0IE with what? What should I write to enable TMR0IE? Yes, I have to write it with the value 1. And TMR0IF is the name of the flag bit. So here we took the flag bit just as TMRIF. So with respect to timer 0, it is TMR0IF. Okay, so that is the flag bit name. Then you know GIE already, it's global interrupt enable bit. So let us now concentrate on configuring the option register first. Now we will start with the configuration of option register. So we already have a program written for it. Let me just load that program to the MPLAB IDE. So the same program what achieved here, this we generally wrote, but this time we are going to do it with the help of timer 0 module. The only difference is instead of TMR, we write it as TMR0. Instead of TMRIF, we write it as TMR0IF. Okay, that's the only difference. Wait till Alright, so let me close this project and I'm going to open a new project. I mean the one which is already returned. Okay. So open project and I'm going to open something from the timers. So here under timer sources, we have a project by the name 1 second timer. So I'm just starting it off. Okay. Now to start with, we will go with 1 second timers generation. So first, if you can see, I have two header files. One is main.h, the other one is timers.h. Then under source files, we have timers.c, main.c, isr.c. Now first we will see main.c file. So first we have the init config function return. In the init config function, basically we have done the initialization of LEDs. So because I'm going to toggle an LED, so I am going to have the LEDs turned off. So LED array is returned with 0x00. LED array is just representing port D and its data direction register is tris-D, which is returned with 0x00 again. Then I'm doing the initialization of the timer 0 module by calling the init timer 0. Now what and all should I do the initialization is, I have done the initialization in a separate .c file, that is timers.c. Now what and all initialization I have to do is, I have started with option register, okay, one of the register associated to the timer 0 module. This option registers first 2 bits. So they do not belong to the timer 0 module, so you don't have to focus on that. Now above every bit, you can see something written as r/w, r/w. Do you know what does this r/w represent? Yes. So r represents read and w represents write. So if there is r/w return, that means that particular bit is readable, that particular bit is writable as well. So if you want, you can read from that bit. If you want, you can also write into that particular bit. So r/w return will represent readable as well as writable. Along with that, you can see a 1 or a 0. Okay, so along with that, sometimes you see a 1, sometimes you see a 0. So that represents the default value. Okay, if there is a 1, default it is representing 1. If there is a 0, by default it is representing a 0. So it is representing a default value. Okay, then apart from that, so the next you have got is with respect to the bits here, bit number 7 is RVPU, bit number 6 is INT EDG. They do not belong to the timer register. Then coming to the T0CS, so this is the bit you are going to tell whether you are going to make use of the internal clock or you are going to make use of the external clock. So if you are configuring timer as a timer, you have to make use of internal clock. If you are configuring timer as a counter, you have to make use of an external clock. So as of now, my focus is to configure timer as a timer. So I have to make use of internal clock. To choose the internal clock, what should I write T0CS with? What should I write T0CS with? Yes, I have to write it with the value 0. By default, it is having the value 1. So I am writing T0CS with the value 0. So that is to choose internal clock. Then T0SE is to tell if you are using external clock, Whether it is the rising edge or the falling edge, you have to specify. So T is timer 0 source edge select bit. As of now, we are using internal clock only. So you don't have to be worrying about this bit as well. Then PSA is prescaler assignment bit. So whether you want the prescaler to be assigned or not, you are supposed to say it with the help of PSA bit. As of now in our calculation, did we use the prescaler? Did we use any prescaler in our calculation? No. So we did not use any prescaler in our calculation. So what do you think PSA has to be returned with? If I don't want the prescaler to the timer 0 be assigned, so I can let the prescaler assign to the WDT. Anyways, watchdog timer we have disabled. So adding a prescaler to the watchdog timer doesn't make any difference. So I have to write PSA with the value 1. Okay. By default, it is anyways 1. So I don't have to overwrite. But if you want, you can overwrite that. Then PS2 to PS0 is to select the ratio of prescaling, whether I want 0, 0, 0, 0, 0, 1, 0, 1, 0. So whatever prescaler rate I want, so accordingly I have to load the values. So in this program, I'm not using prescaler, so I don't have to concentrate that as well. So what else is left with this? So PSA prescaler assigned with watchdog timer. So I just have overwritten. It doesn't make any difference. And initially when the timer 0 has been turned on, I have to write TMR 0 with the value 6 according to our calculation. So before while of 1, once the timer is turned on, I had to write timer with the value 6. So that is written here in the initializing function. And because I want the interrupt to get generated with respect to the timer 0 module, I have to enable it. So TMR 0 IE is written with the value 1. This is to enable the timer 0 module's interrupt. Any doubt in the initialization of timer 0 module? Okay. And apart from that, in the main function, that is in the init config function, I also have to make sure GI is returned with the value 1. So any source of interrupt you are configuring, you have to make sure GI is returned with the value 1. So that is global interrupt enable bit, which has to be returned with the value 1. So I have GIE returned with the value 1 here. Okay. So after that, coming to the main function, I have init config function return, the function call, nothing return inside the while of 1. So for every 250 ticks, interrupt gets generated, control goes to the ISR. So there is a variable called count taken, which is of static unsigned integer return with the value 0. So after that, if TMR 0 IF is equal to 1, okay, so if TMR 0 IF is equal to 1, I have to enter. So here we have written TMR is equal to TMR plus 8. The reason why we have written 8 here is, actually we had to write TMR is equal to TMR 0 plus 6. This addition takes one more instruction cycle after the operation. This assignment takes one more instruction cycle. So that is why we have written TMR 0 plus 8 instead of 6. Okay. I had to write TMR is equal to TMR plus 8. Then I'm checking if count is equal to 20,000. Count is updated to 0. LED is returned with its toggling, and TMR 0 IF is returned back with the value 0. So no change in the program what we wrote here. So things are being exactly the same. And once you take the action, control will come back to the main function. For every 250 ticks, control will go to the ISR. It is going to check if it has achieved count as 20,000. only then the toggling of the LED is going to happen. Let me build this code and show you the output. So I'm giving the build project. Meanwhile, let me open the Pixim lab. Okay. So I'll go to file, load hex, then under timers, timer sources, 1 second timer, then distribute, default, production, the hex file. So you can see for every 1 second, the LED is being toggled. 1 second, LED is on. After 1 second, LED is off. Again, after 1 second, LED is on. 1 second, LED is off. So if you are not sure, you can monitor it with the help of your phone also. For every 1 second, you can properly see the toggling of LED happening. Are you able to observe the output? Any doubt with this program? Okay. Now, if I go with the pre-scale of 1 is to, let's say, 16. Okay. So tell me, if I use a pre-scale of 1 is to 16, what will be the value of count for the same 1 second of time? If I use a pre-scale of 1 is to 16, what will be the value of count? Please do the calculation. For the same time of 1 second, if I choose a pre-scale of 1 is to 16, what will be the count? Anybody there who did the calculation? Count divided by 16, how much is that? If I use a pre-scale of 1 is to 16, what will be the value of count for the same time? In the place of scale, you just use 16. Yes, 1250. Okay. Now, for me to choose the pre-scale of 1 is to 16, look at this. What all the changes should I make? To choose the pre-scale of 1 is to 16, what are the changes I have to make? Okay, so first PSA has to be written with the value 0, right? Then how to choose pre-scale of 1 is to 16? What should I write PS2 to PS0 as? Yes, so I should write it as 0, 1 and 1. Okay, PS2 is 0, PS1 is 1, PS1 is 1. So I have to write 0, 1 and 1. Okay, PS2 has to be written with 0, PS1 has to be written with 1, PS0 also has to be written with 1. Now observe the same program here. We have tried achieve 1 second of time with the help of a prescaler also. So I'm opening another project. So there is 1 second timer using prescaler. The only difference is in the initializing function. So if you look at the main function, there is no difference. Okay, no difference in the main function. No difference in the ISR function except this count taken as 1250. Okay, so count we have taken as 1250. Coming to the timers. T0 CS as usual, we have it written with 0. Prescaler, I have to assign it with to the timer 0. So I've written PSA with the value 0. Then prescaler setting for 1:16, PS0 is written with 1, PS1 is written with 1, PS2 is written with 0. And timer 0 is written with 6. Timer 0 interrupt enable is written with 1. So that is the only change you can see in the prescaler. Okay, you are going to choose a prescaling value. Now I'm going to build this. So this time control comes to the ISR a little late. So only if you visit the ISR for 1250 times, you will be covering 1 second of time. So you are going to toggle the LED at that time. So build is being successful. Let me load the hex file. Sorry, I'll go to file, load hex. Then after this 1 second timer with the prescaler, distribute, default, production, the hex file. So you can still see the toggling of LED for every 1 second, but this time we have used the concept of prescaler. So because our timer 0 module had the option of prescaler, we choose a rate of 1:16, and accordingly we updated the count to be 011, count to be 1250. We updated. So pre-scaling we chose 1:16. So we loaded that prescaler value to the registers of the timer, the bits of the timer register. Then now if you see, the toggling of LED is again happening for every 1 second, but we are using the concept of prescaler as well. Understood this? Okay. Now we have multiple timers in case of our microcontroller. We have 3 timers. There's timer 0, timer 1 and timer 2. So when it comes to the timer 0 module, as I said, timer can be configured as a counter as well. So how to configure the timer as a counter, we will see it later. But we have one more timer to be configured. So apart from timer 0, timer 1, timer 2, you configured timer 0. Configuring timer 1 is a part of your assignment. Let us configure timer 2 module. Okay. So we are going to achieve 1 second of time with the help of timer 2 module this time. Now, there is a special feature in the timer 2 module. Let me take you there directly to the timer 2 module. So this is your timer 2. Okay. So in case of your timer 2 module, I will ask you to read maybe this much. So please read how much ever I have selected and let me know once you're done reading. Okay. Fine. Let us continue. So if you actually see here, what is the resolution of timer 2 module? What is the resolution of timer 2 module? It is again 8 bits, same as that of timer 1, timer 0. Timer 2 also has a resolution of 8 bits. And what type of scaling does timer 2 support? What type of scaling the timer 2 supports? Yes, it supports both pre-scaling and post-scaling. So in case of pre-scaling only, you have got three rates. One is 1:1, 1:4, and 1:16, which can be selected with the help of these two bits. Okay, so T2 con registers 2 bits you can use, and you can see the input clock. This is how we found how much is the clock or how much is the size of the or how much is the time it takes for one instruction to get executed. So it is 4 divided by f oscillating frequency. So clock here is f oscillating frequency divided by 4. Okay. So timer 2 is a 8-bit timer which supports both pre-scaling and post-scaling. Apart from that, it can also be used in pulse width modulation. So we will see it later. How is it useful in pulse width modulation? The timer 2 register. So the name of the register is TMR2. It is readable as well as writable. The pre-scaling options you have is 1:1, 1:4, and 1:16. Next, apart from that, the timer 2 module has an 8-bit period register, which is nothing but PR2. Okay, so timer 2 module has an 8-bit period register. Apart from all other registers, the speciality of a timer 2 module is it has a special register called PR2 register. So what is the usage of this PR2 register is? Earlier in the previous program, when I had to get the interrupt generated after 250 ticks, I had to preload the timer register with some value. But here I don't have that problem. If I want the interrupt to get generated in just 250 ticks, I just have to write PR2 with the value 250. Because if you take the timer 2 module, it is going to have the tick done until it reaches the PR2 register's value. If PR2 register value is returned with 250, an overflow happens after timer 2 module reaches 250. If you have written PR2 with the value 5, an overflow happens after TMR2 has reached the value 5. So if you want the interrupt to get generated after certain number of ticks, you can write PR2 with that value, or by default it will be returned with 255 only. That is FFH. Okay. So that is the only difference in case of timer 2 module. So you can see if you want to choose the post scaling option, you have to write it with the help of T out PS3 to T out PS0. So you have the scale of 1:1 to 1:16. So 1:2, 1:3, 1:4, 1:5, 1:16 you have. So if you want the post scaling of 1:3, you just have to write 0:0:1:0 here. If you want the post scaling option of 1:16, you have to write 1:1:1 here. 1:1:1:1. Okay. Then apart from that, if you want pre-scaling option, you can go with T2CKPS1 to T2CKPS0. If you write 0:0, you're choosing a prescale of 1:1. If you write 0:1, you're using a prescale of 1:4. If you write 1 with a don't care, so X means don't care. You can either write a 0 or a 1. If you write 1 with a don't care bit, then you are using the prescale of 1:16. Then, in case of timer 1, once you configure the timer 0, that was turned on automatically. But in case of timer 2, you have a special bit to turn the timer on whenever it is required. That is TMR2 on. So TMR2 on return with the value 1 is going to turn on the timer 2. TMR2 on return with the value 0 is going to turn off the timer 2. So that is it with respect to the timer 2 module. Let me load the project of timer 2. So we are going to achieve 1 second of time with the prescaler, but this time we are using timer 2 module. So program wise things are going to remain the same. So it is 1 second prescaler, sorry, not this. It is not this. Let me open 1 second timer with timer 2. So you can see the main function. There is no difference in the main function. Okay. So GIE is written with the value 1. Then LED is being configured. So for the timer 2, you also have to enable peripheral interrupt enable bit. So PEIE has to be written with the value 1. That is peripheral interrupt enable bit. Then main function is remaining the same. If you look at the ISR function, because we are using a prescale of 1:16, we are writing count with the value 1250. So timer 2's flag bit is TMR2IF, which is written with the value 1. TMR2IF is written with the value 0 after taking the action. If you look at the initialization of timer 2, so we also have initialization of timer 0 return here, which you can erase if you don't need. If you come to the timer 2, we are using a prescale of 1:16. So T2CKPS0 is written with 1 and T2CKPS1 is written with 1. This exactly is a don't care bit. We have written it with 1. We want the interrupt to get generated for every 250 tips. So PR2 is written with the value 250. Then timer 2 interrupt enable bit is written with 1 and timer 2 on. It's a bit which is used to turn on the timer, that is also written with the value 1. So this is the initialization of the timer 2 module. Let me build this and show you the output. You will see the same output. Script engine is not supported. Okay. So this build is not giving me the same. Actually, let me close the IDE and open again. So sometimes the IDE will not behave according to our requirement. So that is why. Meanwhile, let me just give you the attendance. So we have to see that output. Please wait. Don't mark your attendance. Leave off the session. To see the output of the previous program. So here is your QR. Please have your attendance mark. And please do wait. I still want you to see the output of the previous program. Okay, I'm saying that you don't have to quit. I'll not give the attendance. So I see people attending the class only for the sake of attendance. Guys, if you people are doing it, then please don't join the session for the sake of attendance. I can give the QR somewhere in the middle of the class also. Okay. So we see some of you are joining in between and leaving off. So let me wait. You please wait for the QR if you want, because as I said, I want to show the output also. Okay, so build is going on. Am I not properly audible? Audible? Okay. Yes, so let me show you the output of this one last program for today. So this is with respect to the timer 2, distribute, default, production, the hex file. You can see the toggling of LED which is happening for every 1 second. Okay. And this time we are making use of timer 2 module and also a prescale. Ma'am, if we want to see the printf statement in serial port, is it possible? In the MPLAB IDE, that is not possible. So IDE is just a tool you are using to have your program written. The output on the IDE. So seeing the output is not possible. So in that case, if you want serial port, yes, you can make use of UART. There is a serial port available. So there is QtCom, a separate like tool which is already installed. So you can make use of that in order to like use it. TMR0IF and TMR0IE in timer 0. Can you tell its function? I missed that part. So TMR0IF is name of the interrupt flag associated to the timer 0, and TMR0IE is the name of the interrupt enable bit. To turn on the timer 0's interrupt, you have to write TMR0IE return with the value 1. And to know if you came to the ISR because of timer 0, you have to check TMR0IF is equal to 1 in the ISR. So that is timer 0 and timer 1. Timer 2. Configuration of timer 1 is a part of your assignment, which you can do it on your own later. There is one last program which we are left with respect to the timers. We will finish it off tomorrow and then we will start with the next peripheral. Hope today's class has all been clear. Here is your QR. Please have your attendance mark and then quit the session. Thanks for attending. We will continue tomorrow. Thank you all.